Okay, so let's start. Today we will talk about probability. Okay, okay. So before we talk about probability, we have to discuss random process. So the things that happen in natural can be assumed as a natural process. Okay, even a random process. Even sometime a process, if a process is not that random, we can even assume that is the case, and that is a random process and proceed. So what is a random process? Okay, uh, so they define that if we know what outcomes can happen, then we call it as a random process. But we don't know which particular outcome will happen. Okay, we know all possible outcomes that could happen, but we don't know which specific one that will happen. For example, here, like a coin toss, okay? There is head and tail, and we don't know which will turn up if we toss the coin. And then again, there is these dice from 1 to 6, 6 face dice. So we know that the numbers are from 1 to 6, and then if we roll the dice, we know one number will turn up, but we don't know which one specifically. And again, this is the iPod. Okay, I think you already okay. Anyway, so there is a random shuffle for any music player. That is also a random process. You know the list of the music, but you don't possibly know which will turn up. And again, like the stock market, these are the same random process. Okay, so let's go to probability. Okay, what is the probability? Okay, so a little bit of denotation. So we call it P or A. It's a probability of event A happening. Okay. Again, there are several possible interpretation of probability, but we will discuss two. Okay. Anyway, all these must follow this principle that the probability should fall between 0 and 1. Okay. All probability values should fall between 0 and 1. Okay, so I think we discussed this a little bit the other day, that there are two major approach to probability. Okay, the first one is frequentist approach, which we will use in this class, and another one is Bayesian approach. Okay, so okay, let's see what is a frequentist approach. Frequentist approach is the probability of an outcome, and which is defined as the proportion of time, okay, the outcome would occur if we observe the random process an infinite number of times. So I think it's a little bit difficult to understand, but that is how they write this in statistics book. So to rephrase that, we already explained this the other day. So if we repeat a trial, or if we repeat an experiment many times, okay, frequently, that is called a frequentist approach. And then we know that how many times the outcome would occur. That is the probability of an outcome. For example, if we toss a coin, we know that there is a head and there is a tail. Okay, so even without tossing the coin, we know that probability of getting a head is half. Okay, 1/2. Why do we know that? Because we know that there are two outcomes, two possible outcomes, and we know that one is likely to turn up. Okay, so that is tossing the coin one time. Okay, what happens if we toss it 1,000 times? So if we toss the 1,000 times, that is the same as this phrase, okay? If we observe the random process an infinite number of times, and then we will see that the proportion of getting ahead, approximately equal to 0.5, okay, 50%. If we do it 1,000 times, or if we do it infinite time. So that is the probability distribution from a frequentist approach. Okay, so what if we what about Bayesian approach? So you can see that Bayesian interprets probability as a subjective degree of belief. So there is a subjective term, okay? So lastly, we recently we have our computation technology is really advanced. So and that's why this Bayesian approach is nowadays possible to calculate. So that's why this become a little bit popular. Okay. Now, what is a Bayesian approach? Bayesian approach is the probability taken as a subjective belief. Like we discussed the other day, you gave it a prior probability. Okay. You give a probability based on your experience or anything subjectively, okay? And then you feed it into the model or whatever you are building, and then you generate another probability, okay? That is called posterior probability. Then you do it repeatedly. Okay, anyway, we're not going to cover Bayesian approach, and we are going to talk about frequentist approach. Okay, so there are two. Wait, notation. Okay. Okay, so we talked about it that the frequentist approach use the random process in an infinite number of times. Okay, so that is where lot of larger numbers came in. Okay, what is lot of larger numbers or law large number? Okay, law large number, and this is basically one more observations are collected. The proportional occurrence of a particular outcome converges to the probability of the outcome. Okay, so you see the first part of the paragraph is the proportion. The second part of the sentence is probability. So what's the difference? Okay, and mathematically, I mean numerically, there is no difference. Okay, proportion of getting ahead in a tall square is also half or 0.5. Probability of getting ahead in a tall square is also 0.5. But the interpretation is different, okay, between proportion and probability. So proportion is just a proportion. In a probability, that is in a sense of being most likely. So interpretation is different, but the number is the same. So basically, it means that when you do something repeatedly or in an infinite number of times, then the proportion of getting something converge to the probability of getting that outcome. So in our coin toss example, okay, this example is rolling dice, okay, not tossing coin. So you can see that we have 1 to 6, 1 to 6 possible outcome. Whenever you roll a dice, one outcome will happen, okay, from 1 to 6. Okay, say you roll the dice 5 times, then you're not sure that that the number 1 will time a certain number. Okay, say let's calculate that we already know each possible. Wait, okay. What is the probability of getting one number? Okay, what is the probability of getting 2? Okay, probability of getting 2 out of a roll dice, rolling a dice is 1 by 6. Okay, There are 6 possible outcomes and then 1 result. Okay, whatever it is, okay, from 1 to 6, we get 1 minus 6. That is the outcome. But when you roll the dice, okay, 5 times, there is not likely that 2 will be in that outcome. Okay, because we got only a few number of time. But that number will increase as your sample size increase. That's why your sample size is important. So you see the x-axis indicated number of rows. Okay, so say we roll the dice 1 time. So it's the probability of getting an outcome out of 6 number is approximately 0. You see, so even up to 5 or 6, it is 0. And then as the number of rolling dice increases, that probability of getting something, okay, probability of getting an outcome approximately converge to 0.16, which is exactly 1 by 6. And that is basically called our large numbers, okay? Anyway, you have to remember, as your sample size increase, proportion converge to the probability, okay? Proportion becomes equal to the probability of the outcome. Okay, that's why when we conduct a study, we should have enough sample to do any inferential statistics. Okay, so let's take a quiz here. Which of the following events would be most surprise you by A, B, or C? Okay, so which one? A is exactly 3 heads in 10 coin flips, and B is exactly 3 heads in 100 coin flips, and C is exactly 3 heads in 1,000 coin flips. Which would surprise you? What do you think?
C.
Yeah, C. Anybody choose A? No, I guess not, right? Because when you do a 10 coin flips, then you can have 3 heads. That's not surprising. And even if you do 100, you can get exactly 3 heads. But it is less surprising than number C, which is exactly 3 heads in 1,000 coin flicks, which is rarely happens. Okay, unless your coin is, unless you do something to the coin. Okay, next. Now let's talk a little bit about coin toss. Okay, say you toss a coin 10 times and it lands on head each time. What do you think the chance is that another head will come out on the next toss? Okay. Okay, so here is the question. So you toss a coin and 10 times, and every time you get head. So what do you think the next the 11th time when you flip the coin, what will happen? Okay, it is very common when you do something as gambling. Okay, so the probability is still 50 times because you don't know which will turn up. Okay, head or tail, you don't know which will turn up. So probability of getting head on 11 toss is the same as probability of getting head on a 10 toss, which is half. And because the coin is not due, I mean, there is no due date. Okay, there is no due 10 because whatever you get on the 10 toss is independent. It's not getting you tail on the 11 toss. Okay, so it's not related to each other. So that's why it is called the gambler's fallacy. Okay? It's a fallacy because or you lose at certain times, and then the gamblers would think that, okay, next time I'm going to win big. So the probability is still the same. Okay, so this is common misunderstanding. Okay, anyway, here is the key point. Here is when you toss a coin, we think it as a trial, okay, or as an experiment. Okay, so one experiment is independent of the next experiment, because whenever you toss a coin and get that value, get the outcome, it's not, it has nothing to do with the next time. So we will talk a little bit about disjoint events, okay, and then general addition rule for probability. Okay, anyway, we will talk about this. We will talk about sample space, probability distribution, and complementary events. And okay, so I think you may hear this term from your experience, mutually exclusive. Okay, so what is disjoint? Is mutually exclusive, the same meaning. Okay, so let's look at this. There is a Venn diagram of A and B, so they do not touch each other. Okay, there is no intersection between each other. So which means that whatever it is in A, whatever it is in A, it's not associated with B. Okay, so probability of getting A and B at the same time is 0. Okay, because they are the opposite. Okay, they cannot join. So that's called disjoint. Okay, they are not join each other. That's in other terms, it's called mutually exclusive. Okay, so events cannot happen at the same time. So let's consider as with a coin flip. Okay, so when you flip a coin one time, the outcome can be a head or a tail. Okay, it cannot be both. And student cannot both fail and pass a class, as well as a single card drawn from a deck cannot be an ace and a queen. Okay, that is if you play cards, you will understand this. Otherwise, just understand this one. Okay. Okay, non-disjoint. Okay, this is the opposite of disjoint. Okay, non-disjoint mean they have some intersection. So some events can happen at the same time. Okay, so A and B, and they can happen at the same time. So probability of getting A and B is not 0. Okay, it's not nothing. There is something. So here's an example. So a student can get an A in statistics as well as an A in economics, okay, in the same semester. Okay, so based on the context, based on the problem that you are solving, it can be a disjoint event or non-disjoint event. Okay, let's look at this one. I think it's a little bit, this is the union of disjoint events. Okay, so how do we think about it? Think about this. Okay, so these are the deck of cards. Anyway, we're not testing your knowledge of cards. Well, what we are trying to do is we're trying to look at the probability. Okay, because these mathematics probability are coming. A lot of people from gambling, they trying to think about probability and come up with this theory and everything. That's why they are part of this learning process. Okay, so and what is the probability of drawing a jack or tree from a well-shuffled full deck of cards, which means it's a random process. Okay, it is not rigged. It is not ordered by somebody. So it is a well-shuffled. So this is a random process, and we draw a jack and a tree. So what is the probability? Okay, so here's a jack, and then here's a tree. So the way we are doing this, that probability of getting jack, and we look at probability of getting tree. Okay, so they are not intersecting with each other. So basically, basically there are 52 cards. Okay, if you count this, there is 52 cards, and then 4 cards are jack, and 4 cards are tree. So okay, so probability of getting the jack is 4.52, and probability of getting tree is 4.52, and they do not intersect with each other. So we don't have to consider about intersecting part. Okay, so for disjoint events, when we turn this into mathematical formula, we get this probability of getting A or B, man, that probability of A and plus B. Okay, this is called a additive rule of probability. So additive rule is OR. Okay, remember this one, OR. So for disjoint events, which are mutually exclusive for each other, we got this formula. Next, we look at this union of non-disjoint events. Okay, so what is the probability of drawing jack or red card from a well-shuffled full deck of cards? So we want jack and we want red cards. So in a jack, we got 4 jack. Okay, for red cards, we have these 2 rows. Okay, so we look at the probability of jack and probability of red. So we calculate probability of jack for 52. That is what we have learned. And probability of red, and that is 26.52. But if you look at this, we have intersection area. Okay, so we delete this from the probability. Okay, because it's already included in the. So we talk about probability this one, probability this one, and if we add in that, this portion where we double. Okay, so we don't want that, so that's why we are subtracting that part again. So that's why probability of jack and red is 2. 2 cards are both jack and red, so that's why we are subtracting this probability of joint event. So basically we got 53.8%. Okay, so for it, when we turn this, we got this one. Probability of A or B turns out to be probability of A plus, probability of B minus probability of A and B. So here the context is the context matter here. So if the events are non-disjoint, you use this formula for additive rule. Otherwise, if events are assumed as disjoint, then you use probability of A or B equal probability of A plus B. Okay, you don't have to subtract it. Okay, so this is a general additive rule. You don't have to remember everything, just remember this. Probability of A or B is probability of A plus probability of B, and then subtract the intersection part. But when the events are disjoint, which basically means there is no intersection part, you don't have to, this one is 0. Okay, so you can put it or you can leave it. Anyway, this where is 0. Okay, so that's why the formula simplifies to P or A or B equal to P or A, probability of A plus probability of B. Okay. Okay, so far we talked about the random process, we talked about law of large numbers, then we introduced the probability using coin flicks and drawing deck of cards. Okay. Next, we are going to look at the sample space. So what is a sample space? A collection of opposite outcomes. Okay. In our coin flip, we have the sample space head and tail. In our rolling dice, the sample space 1, 2, 3, 4, 5, 6. That is if we do it one time. Okay. Okay. So what about we do it 2 times? Okay. We toss a coin 2 times. So we got head for the first time, and then probably we will get head or tail in the next time, the same way. Okay. Okay. So here's an example. So a couple has 2 kids. What is the sample space for such of these kids? These kids. For simplicity, assume that such can only be male or female. Okay. So anyway, let's try to do this. Okay. If when we think about sample space, we think of all possible outcomes. So the two kids can be male, okay? The two kids can be female, so that's why MM and FF. And then the first kid is male and the second kid is female, or the vice versa, okay? So we have FM and MF. So that is called the sample space, okay? Okay, so sample space is just basically every possible value. So it's a set, okay? So it's denoted by curly bracket. And then we got our sample space because we're going to use the sample space in our probability distribution, okay? So that is the probability. And then if we want to look at the distribution of that probability, we need to know the sample space. Okay, so probability distribution lists all the possible outcomes in the sample space and the probability in which they occur. So let's take a look at two examples, okay? Okay, let's flip the coin one time and then two times. Okay, so for one toss we got head and tail. So yeah, for each probability we got half. Okay, 0.5. What about two toss? Okay, this is the same as having two kids. In previous example, okay, where we got head, tail, head, tail, head. So these are subspace of 4, okay, and then one event have okay, probability of having one event out of 4 is 1/4, 0.25. Okay, so here's a little bit rules for probability. Okay, we now know that events listed must be disjoint. Okay, if one event happens, the other cannot happen. Okay, for the events. For the probability, must be 0 and 1. We already know this. If we sum every probability of the events, then it should sum up to 1. So this is basic probability. And then next, we're going to talk about complementary nature. Okay, and complementary events are two mutually exclusive. Okay, so they are the opposite events. Okay, and then if we sum these probability, they should add up to 1. Okay, in our case, the complementary of head is tail. Okay, the complementary of tail is head. So should have if we sum these probability, it should add up to 1. Okay, then in this case you can take any value, okay, and then the opposite of that value will be complementary value. So two toss we take we complement head and head, and then the rest in the sample space become complementary events. Okay, so the probability of 0.25 and then the probability of complementary should add up to 0.75. Okay, so if we sum these two probability, it should add up to total up to 1. Okay, so these are very basic probability theory. I think we already know this since our high school, and it's easy to understand it if you think about, you know, tossing coins and rolling dice. Now, how can we know that if two events are independent of each other using probability? Okay, we're going to discuss this uh, in this session. So we'll discuss independent events, okay, and then how can we assess independence and multiplication rules for independent events. Okay, so before this, we talk about disjoint events which are disjoint or non-disjoint, okay? And now we talk about independence or dependent events. Okay, so what is independent? So two processes are independent if knowing the outcome of one provide no useful information about the outcome of the other. Okay, if we know one outcome happens, and then you can guess what will happen next, then it is called dependent. Okay, if we know one outcome and then you know nothing about it, has nothing to do with the other outcome, then it is not independent. It is not dependent. So let's consider with our tossing coin. Okay, so when we toss the first time, we got We got one outcome, okay? And then when we toss second time, we can get either head or either tail. We don't know, okay? When you get head on a first toss, you cannot say we get another head on the second toss, okay? If we assume that, that is called gambler's fallacy, okay? Anyway, so knowing the outcome of the first toss did not provide us any useful information about the second toss. And that's why these outcomes are independent. Okay, these trials are independent. Okay, what about a deck of cards? We know the deck of cards 52 cards. So when you draw one card for the first time, we got a red. Okay, and then you draw the second time. So you know that the probability of getting this card reduced. Okay, reduced to 3. Okay, so outcomes of to draw from a deck of cards. That is without replacement. Okay, so here is really important, without replacement. So there are dependent. Okay, because you know one outcome and then you can predict something, you can know something on the second outcome. It is called dependent. So how do we check for independence? So this is how you write probability of getting A given B, okay? So when we know some outcome and then we want to know another outcome. So if probability of getting A given B is the same as probability of A, then A and B are independent, okay? So what is the meaning? The meaning is whether you know B or not, okay? Whether you know which outcome you get, the probability of A is the same, then these providing B does not have any values. So if that is the case, then A and B are independent. So let's take a look at this. So in 2013, Survey USA interviewed a random sample of 510 this NC, not I think Northern Carolina residents, asking them whether they think widespread gun ownership protects law-abiding citizens from crime or makes society more dangerous. 58% of all respondents said it protects citizens. So that is what 58% of all respondents said. And then 67% of white people think that, okay? And only 28% of black people think the same. And then 64% of Hispanic respondents share this view. So basically, the question is, opinion on gun ownership and race ethnicities are more likely what? A, complementary, B, mutually exclusive, C, independent, D, dependent, and E, disjoint. Okay, I think you should become familiar with this term. So let's think of one by one, okay? So let's take a moment, and the time is almost up, so I'm going to stop this and rejoin the meeting again. Okay, let's think about this, and then when we started. Okay, so what do you think, which is the right answer? Okay, I think everybody's here. Okay, so let's go forward. So we can think like this, okay? Probability of protecting citizen and probability of everybody thinks that it protects citizen. Okay, somebody answer. What is C? Okay, let's see. Okay, uh, okay, let's see. Uh, probability of gun ownership protects citizen is 0.58. Okay, then we have probability of this one. Okay, probability of protects citizen given white is 0.67, black 0.28, and then Hispanic 0.64. So anyway, when you think about this, okay, 0. It does not add up to 0.58, and it's also varied based on the ethnicity. Okay, so we talk about this. Probability of A given B is equal to probability of A, then we can say that it is independence. Okay, so if we want to say that gun ownerships and ethnicity are independent, if we want to say that, then we should prove the probability of protected citizen is the same as probability of protected citizen given anything. Okay, so that is not the case here. So that means that these probability are not the same. So the answer is D. Okay, this is dependent events. So based on the ethnicity, the probability of getting citizenship, the probability of people thinks that gun ownership to the citizen varies. Okay, so it means that gun ownership and race ethnicity are dependent, okay, or related. In our case, it is associated. Okay, so the same as dependent. In statistics, we call it dependent. Okay, how do we determine based on some of the data? So we calculate something called conditional probability. Okay, that is what we seen earlier, probability of K given B. So that is conditional probability. So we look at the difference. Okay, and we look at the difference and see, say there can be a dependence. We cannot exactly sure. And then the next step is we are going to test hypothesis test. Okay, that is where inferential statistics can be. And then if the difference is large, we can say that there is strong evidence, okay, that the difference is real. If the sample size is large, even a small difference can provide strong evidence of a real difference. Okay, so I would take a moment here and explain to you that the difference between statistical significance and predicate difference. Okay. Okay. So say that okay, let's talk about the BMI. Okay. So say you have a clinic and you have say HIV patients. Okay. So usually HIV patients, they are malnourished. So you implement a nutritional support program. Basically, you provide these patients nutritional supports and see next 6 months how is their BMI doing. Okay, is there a change or is there, you know, BMI is no difference. So you did a baseline BMI assessment, and then 6 months later you did the same BMI assessment again, and then you compare the two BMI difference. Okay, so okay, hypothetically speaking, say you found a difference of BMI difference of 5. Okay, say the mean BMI difference is 24, and then when you give it, it jumps to 29, and your sample is 100, and then when you run a hypothesis test, whether this difference is whether if it is the real difference, then the test say the p-value is greater than 0.05. Okay, okay, and then you collect you do the same study on 10,000 HIV patients. And then when you did it again, your p-value becomes less than 0.001. Okay, but you got the same difference, 24 and 29. So that is why sample size, we want the sufficient number of sample size, but we do not want, everyone. We do not want a very large sample size, because even once you pass the sufficient point, sufficient sample size, then the only difference is your budget, your resource, and then the p-value, okay? When you got a really big sample size, your p-value will become very small. So when you did something like looking at the risk factor, every risk factor becomes significant, okay? Because there is a large sample size. And then we will talk about in later session why sample size and the p-value has a relationship, or the 95% CI has a relationship, okay? And right now, if your sample size really large, a small difference can provide strong evidence of a real difference, okay? Okay, I will give you another example. Let's take a moment here. And if you think about potassium, okay? If you think about potassium level, even a decimal change uh, can be should be careful, right, with a decimal change. So if there is an absolute number change, like potassium level from, say, from 9 to 6, then or 6 to 4, then there is a problem, okay? Because the potassium level vary with a very small number. Okay, so in this case, you got a 100 sample size, and then you look at the potassium changes when you give certain drugs, okay? And then
can you please share the screen? I think we are stuck in.
No. This is a screen. I'm just giving you an example. I just want to I don't know if I am making you confused, but I'm just giving you an example. But this will be, I think we will discuss this more when you talk about the later session, okay? Okay. The screen is not frozen, okay? I'm just talking out of context.
Thank you.
These are not on the slide. I just want to explain, because this concept is really important when we do data analysis, okay? Because, well, okay, say when I was a beginner, I just wanted to look the p-value, and if it is significant, I'm happy, okay? So I just want you to know that p-value does not carry that weight, okay? As a researcher, as a doctor, as someone who know the context, you decide what is important, okay? So that's why there is a starting level or subjective, subjective intellects. So that's why how you do your data analysis, okay? Anyway, so say you got 100 sample size, and you look at the potassium level change, and then you see that there is a one-digit change, okay, from becoming from 6, reducing from 6 to 4 of potassium value. So which must be shocking, right? But when you look at a p-value, say you got only 100 sample size, so it's not significant. Okay, so that is the problem. Because based on the sample size, these statistical methods and calculations operates. So that's why whenever you do the study, there should be sufficiently large sample size, okay? That's why I'm emphasizing on that point. You need sample size. Okay, anyway, let's go forward. So earlier we saw that this probability of this probability of say can ownership protect citizen, given the respondent is white, is 0.67, and then when this become Hispanic ethnicity, then it's 0.64. And which sample size would you more convinced for a real difference between the proportion of whites and Hispanic who think the widespread can ownership protest citizen? Okay, so there are two scenarios: when the sample size is 500 and when the sample size is 50,000. So the answer is already given. Okay, when you have a larger sample size, you can be more convinced of a real difference. But in order to get a 50,000, that would be a challenge. Okay, next we're going to talk about product rule for independent events. Okay, so we now know how to check the independent, how to check whether two events are independent or not. So if A and B are independent, we use this one. Okay, probability of A and B, okay, occurring at the same time is the same as probability of A multiplied with probability of B. So when you cross the coin twice, and then what do you think probability of getting two tails in a row? Okay, let's think about it. Probability of getting one tail, probability of getting tail on first toes is half, and then probability of getting another tail on second toes is also half. So using this formula, we multiply half and half. We got 1/4. Okay. So it's just it's a thinking process. Okay, in the same way, we can think about multiple events. Okay, if multiple events are independent of each other, then we can just multiply everything. Okay. Next. Okay, so this is a 2012 Gallup's poll suggests that West Virginia from US has the highest obesity rates among the US states, and with 33.5% West Virginians being obese. Okay, so we now know the probability of being obese, probability of West Virginian given obese is 33.5. Assuming the obesity rate is still constant, okay, what is the probability of 2 randomly selected West Virginian are both obese? Okay, anyway, probability of obese is 33.5. So we randomly select two people from West Virginia. So what is their obesity? What is the probability of getting two people from Virginia, West Virginia are obese? Okay, so let's take a moment here, and then we think about this one. Okay, probability of getting obese is this one, 0.235. And then probability of both obese is probability of first obese and second obese. Okay, and then we think about it. Okay, I think if we randomly select from West Virginia, then probably that whether you pick the first one as obese has nothing to do with the second one being obese. So I think these two events are independent of each other because we randomly select. Okay, anyway, I won't confuse you anymore. Okay, so we plug in these value into our formula. So we multiply this and we got this one. Okay, when you multiply decimal value, the final result you get is less than both value. Okay, so we got 0.11, 11%. Okay, anyway, let's go back to another survey, world value survey, and then they talk about the perception of life, work, family, politics, and then they use a very large number, 77,000 people from 57 countries, and estimated 36.2% of the world population agree with the statement that men should have more right to a job than women. Okay, so only like around 35% agree with this statement, and the survey also estimated this 13.8% have a university degree or higher, and 3.6% of people fit both criteria. So the intersection, okay, this is the intersection between having university degree and who agree this statement is 3.6. So which is fairly low, okay, very low. And the probability of everyone agree is 0.36, okay, 36% agree. Probability of having university degree is 30.8%. So we got an educated at university level is fairly low, okay. 14 people out of 100. And then probability of getting agree and university degree in this session is 3.6%. So the first question, agreeing with the statement, men should have more right to a job than women. Okay, first one, agreeing and university degree are disjoint even. Okay, so let's review this, okay. In order for us to call this the disjoint even, what should we do? What should we have to prove? Okay, so we should have to we should prove that the intersection should be 0. Okay, so easy. The intersection is not 0 in this case. It is 2.6%. So it is not disjoint even. Okay, so the number already gave you the answer. Next, we draw a dry Venn diagram. Okay, summarizing this and their probability. So we did this. Okay, so the agree is blue color, and then the university degree is this yellow color. See, it's not yellow, it's a little bit like red, brown color. Okay, anyway, so the intersection is 0.035, and then those who agree is this one. Okay, 0.326, and then from this end to this end is this one. 0. Okay, here from this end to intersection is 0.36, and then we subtract the intersection, and then we got this without intersection. Okay, anyway, do the same. Okay, this should be fairly easy. And then when we look at the next question number 3, what is the probability that a randomly drawn person has a university degree or higher, or agrees with the statement about men having more right to a job than women? Okay, anyway, probability of university degree or agreement. Okay, so this is all agreement. So we use the general addition rule. Okay, so we got a formula, and then you just plug in the value from this one. Okay, so probability of A and probability of B. So probability of A should be 0.362, and probability of B should be 0.138, and then you got the intersection here, and then you subtract it. Okay, now we got 46.4% get either of these. Okay. Okay, anyway, so I think this or and statement is the same as the condition we talk about in week 1. Okay, these are basically the same. So when you talk about either A or either B, so when you combine them, your value should be at least equal or greater than the individual value. Okay, so that's why we got 46.4%, which is greater than this value. And then when you multiply it, because these are decimal points, you should have a smaller value because of this decimal point, okay, than the individual value. That is the basic concept. So, and question number 4 is, what percentage of the world population do not have a university degree and agree with the statement? Okay. Okay, they don't have a university degree and they don't agree with the statement. So first we look at we state the given probability. So this one is 0.36, and probably a university degree is 0.13, and then we got agree and university is this And agree or university is this, we already calculated that. And we want to look at probability of neither agree or nor university. Okay, so this is the complement of agree or university. Okay, so that's why we subtracted from 1. So we got 53.6, which is the opposite of 0.464. Does it appear that the event that someone agrees with the statement is independent of the event that you have a university or higher? Okay, so they want to know that is there any relationship that they having a university degree and the agreement? Okay, so if they have university degree and then they agree the statement, something like that. So we just stated we want to know we want to know the intersection. Okay, and what is the probability of having A and having B? Okay, so we use this formula and look at probability of agree and probability of university degree. Okay, whether this is equal to the N of the probability of agree and university degree, which we have obtained from the additive rule. Okay, and number 4. So previously we calculate this. Okay, probability of agree and university, we got 0.036, which is a given value. So we plug into this formula, and then we got 0.05, which is not the same. Okay, so we say that probability of A and B should be this one. But if this is not the case, then A and B are independent. Okay, so here we don't have the same value on each side of the equation. So we say that it is not independent, meaning that they have a relationship. Okay, they have an association. And next, number 6 is, what is the probability that at least 1 in 5 randomly selected people agree with the statement about men having more rights to a job than women? This is called the discrete probability distribution. Okay, so discrete probability distribution is at least you have 5 people. Okay, you have 6 outcome, which is no people agree this, and then you have 1 people agree this, 2 people agree this, 3 people agree this, 4 people or 5 people agree this. So what we want is at least 1. Okay, so we take all this value and look at this. Let's say that probability of at least 1 agree is the same as, okay, this the complement of this at least 1 is the same as no one agree. Okay, so probability of at least 1 agree is the same as 1 minus probability of none agree, which is basically probability of disagree. So what we did is we did you can try on this red side. Okay, what is probability of disagree is the same as 1 minus probability of agree, and then you get the probability of disagree for 1%, and then you we got 6 outcome. Okay, so we do not want 5 people, so you multiply this probability 5 times for 5 people, and then you subtract it from 1 minus 1, and then you got this value. Okay, so at least 89.4% do not agree. Oh, sorry, 89.4% chance that at least 1 in 5 randomly selected people agree with this statement. Okay, so some may feel that it is a little bit complicated because it is, and I just want to give you an idea of how probabilities can be useful in solving our daily problems. Okay, it's not the class about probability. Okay, so we're not going to solve every probability and trying to understand and try to make you understand in depth about probability. Okay, we're not going to do that because this is not a class for probability. So at least you have, at least you are familiar with the probability terms. What is probability? What are the events, and what is the sample space, and then how lot or large numbers can give you the, can convert proportion to, can make proportion converge to probability, and how it is important in the upcoming session, like when we talk about central limit theorems and trying to calculate confidence interval and p-value. These concepts are becoming useful. Okay, at least you have an idea of probability, and then we got disjoint event, non-disjoint event, and then we got independence and dependence. Okay, for disjoint events, we use the edited rules for probability, and for independence, we use the multiplicative rule. Okay. Conditional probability. Now let's talk about conditional probability. Okay, so when you have a condition and then you find that probability. Okay, so we need to understand some names. Okay, marginal, joint, conditional probability. What are these? Okay, and then we talk about Bayes theorem. Okay, not Bayesian statistics. Okay, not Bayesian probability. It is Bayes theorem, which is a very popular theorem in probability. I think you all have used this at one time in your life. Okay, I mean in school, probably not in real life. Okay, so Bayes theorem, and then next we talk about the general product rule. So let's discuss about the study. This is adolescents understanding of social class. To study the examining teenage beliefs about social class, and then they take 48 working class and 50 upper middle class. Okay, all 16 years old. And then study design is objective assignments to social class based on several product measures of both patients' occupations, education, and household income. So they ask these points, and then okay, look at your parents' occupation, look at your education, household incomes, and how do you rate yourself? Okay, whether you belong to lower class, middle, or upper class. And then this is the objective assignment. Okay, this is a subjective assignment. Okay, and then they look at their parents' occupation, education, household income, and then they objectively assign the social class. So basically, the outcome is the social class, and then they look at the social class objectively, and then subjectively based on the survey questions, and then trying to see whether these two variables correlates each other or agree each other. Okay, it is agreement. Some of you may encounter this problem as a validity, something like the validation of the survey question or something. Okay, anyway, okay, so let's take a look at the result. So we get the result, which is the on the left side we call subjective social identity, and on the right side it is objective social class position. Okay, which is basically subjective measurement and objective measurement, and we're trying to look at the marginal value. Okay, what is the marginal value? So the question, look at the question. Okay, what's the probability that the student's objective social class position is upper middle class? Okay, they want to know the probability that a student is upper middle class. So we look at the upper middle class here. Okay, it is on a margin. Okay, on a total line. So this is the margin. The total of the upper middle class is 50, and then we divide this number with the total sample size, which we got 51%. Okay, if we look at this carefully, this is basically a proportion, right? But we talk in probable sense. Okay, that's why this is the difference. So we never use the term equal. Okay, probability is always approximately. So in probability term, it is never exactly equal to 0.51. Okay, it's approximately 51%. So this is the difference between the probability and proportion. So basically this is the proportion. And next we look at the joint, okay, the joint value. So we got subjective and objective measurement. Okay, this is the subjective measurement, the blue one, and the brown one is objective measurements. And then the 37. Okay, so look at this. We got both upper middle class and upper middle class in both category. So this is the intersection, and then you can I think you can understand this point. So what is the probability of student objective position and subjective identity of intersecting? Okay, so we can say that 37. Okay, 37 out of 98 to the value, that is the joint probability. Okay. Okay, so now we already talked about the marginal probability and then joint probability, and next we will talk about conditional probability. So what is the condition? Okay, the condition is on this either side. Okay, not so the denominator change. Okay, the denominator is no longer the total sample size. The denominator is become the total value or whatever you're interested in. Okay, so what is the probability of a student who is objectively in a working class associated with the upper class? Okay, so in the objective measurement, they have a working class. They are in a working class. What is the probability of getting upper middle in lower in working class? Okay, so you just take this 8 and the total it becomes 48. This is called a conditional probability. Okay, so think about it. Marginal probability, joint probability, they all use the denominator as the total sample size. They use the total number size as the denominator, and then when it is conditional probability, then the denominator becomes the total sample size of the particular level, particular category. Okay, that is the difference. And we now comes to the Bayes theorem, okay, which is a very famous theorem, which is probability of A given B is the same as probability of A and B divided by probability of B. Okay, so when you look at the Bayes theorem, when you search Google Bayes theorem, when you search Bayes theorem in Google, then you will come up with a Wikipedia page. Read the Wikipedia page. It's a really informative session and how this Bayes theorem becomes like this, and history, and it's really interesting. Okay, anyway, we want to know the probability of subjected upper middle class given the objective working class. Okay, so this is same as joint probability. Okay, so given the working class, what is the probability of upper middle class? Okay, and then we talk about this probability of subjected to UMC, and you just plug in the formula. Okay, probability of subjected upper middle class and objective working class, and divided by probability of objective working class. So, what is the intersection? Okay, what is the intersection? This is the upper middle class is 8. Okay, so this is the marginal probability. Sorry, this is the joint probability, right? Because the total side is 98. Okay, 8 by 98. Now, what is the probability of working class? 48 by 98. And then we got the joint probability. 8 by 48. Okay, the same, right? Sorry, condition and probability. Okay, so Bayes theorem is based on the Bayes theorem is essentially getting the joint probability, sorry, conditional probability by dividing the joint probability with the marginal probability. Okay, so that is basically Bayes theorem. So how are we going to use this? Let's take a look at this example. The American Community Survey is our community survey. Okay, anyway, this 2010 survey estimated 40.6% of Americans live below the poverty line, 20.7% speak a language other than English at home, and 4.2% fall into both category. Okay, so the intersection is 4.2. Those who live below poverty line is 14.6, and then those who speak other language is 20.7. So based on this information, what percentage of Americans live below the poverty line given that they speak a language rather than English at home. So basically, this problem is the conditional probability, right? So condition is they speak our language, and then what is the proportion probability of these people, Americans live below the poverty line. So use the Bayes theorem and then look at this intersection, okay, dividing intersection with the margin of probability. Okay, we look at this probability of below poverty line as speak in English, which is the joint probability, okay, 0.042, which is here. And then we got 0.207, which is right here. And then we got the 20%, okay, 20% live below the poverty line given the speak other language at home. Okay, so anyway, this is the this becomes the Bayes theorem, okay? The product rule is basically this we got from independent events. Probability of A and B is equal to probability of A multiplied with probability of B. This is the multiplicative rule, okay? And then when we think about the Bayes theorem, we can change into something like this, okay? Probability of A and B, that is what we want, okay? And then we put it on the left side, and then we arrange we put every other to the left side, right side. So we got this probability of A and B is equal to probability of A given B, and multiplying with probability of B. So that is how we got the independent rule. Okay. Anyway, we already talked about this. Okay, whether you know the outcome of B or not, it doesn't change the value of A, the probability of A. Then it is called independent. Okay, that's why in independent, this given B statement is not important anymore because they are independent. So knowing B doesn't change anything for A. So that's why independent product rule for independent becomes like the probability of A and B is equal to probability of A of B. But the original general rule is probability of A and B is equal to probability of A given B multiplied with probability of B. Okay, I think time is almost up, so we will stop here and let's continue tomorrow. Okay, do you have any questions? I think we can answer one question if you want. Or do you think it is a little bit difficult or confusing? Okay, anyway, I think this is introduction to probability, so we cannot discuss very detailed about probability and the other slide we will talk about. We will continue tomorrow. Okay.